So if we're dealing with a region that, a solid region that actually has a hole because it's obtained by rotating a region around an axis which is not part of the boundaries, this is how we do it. First of all, we start with the region. Okay, so this time I'm not going to assume that either the top or the bottom are going to be flat, but in fact both the top and the bottom can be two functions of x. We're still going to go from a left limit a to a left limit b, and so what we're rotating is this region here, but this time we're going to rotate it around a horizontal axis that is outside the region, so somewhere like that. Again, I will let your imagination or your visualization tell you what this solid looks like. Let's see if you can think about it. Can you imagine it? Well, this is the best I could come up with in terms of drawing a picture of it. So it looks like something like that. So now again, what is that? Well, again, it's sort of like the region that we had before with the method of disks, but with some kind of irregular hole in the middle. Yeah, maybe that's the head of a plunger. You know, plunger which has been used quite a few times has become a little bit deformed, okay, or is being put into action. Anyway, let's get away from that. So we're looking at the volume now of this region, and we're going to use the same approach. So first of all, we're going to slice this region, and as we do that, we're going to have to consider two aspects of each slice. So we're going to have to look at the part of the slice that actually creates the solid itself on the outer boundary, and the part of the slice that actually creates the hole. So what we're going to do is going to create both of those, or we're going to consider both of those pieces of the slice. Okay? And now we're going to approximate whatever it is that we're going to obtain by rotating that slice around the axis of rotation. First of all, so we have to consider the whole big slice, big radius r. We're rotating that around the axis of rotation, and we get the same slice, the same disk that we got before. But remember that after this, we have to drill a hole in there, and that's where the inner radius comes in. The little radius r will generate a hole, and we have to make sure that that hole is subtracted once we compute the limit. So how are we going to do that? So first of all, we're going to figure out what is the volume of this disc with a hole, which of course we're going to call a washer because that's the shape of a washer. And how do we compute it? Well, that's just going to be the volume of the outside disc, which is a cylinder, minus the volume of the inside disc, which is also a cylinder, and they both have the same height, namely delta x. So what we're going to do is going to start from delta x, which is in common. Then we're going to compute the area of the outside disc, and then we're going to subtract from that the area of the inside disk. So the product of these two elements now, pi r, big R squared minus pi little r squared times delta x, gives us the volume of one slice. What do we need to do next? Same idea as before. That means I'm going to add up all the slices. We're going to end up with a formula looking like this. And then to get this only gives us an approximation still. And then we're going to take the limit as again the number of slices goes to infinity, and their thickness goes to 0. And so we end up with this formula, which by now I hope is becoming a familiar formula. That is the formula that defines the Riemann integral. So it's going to be again the integral from from a to b, where a and b are the left and right limits of, well, the pi is in common, and it can, being a constant, can come out of the integral. So on the inside, we're going to end up with simply big R squared minus little r squared in dx. So this is what we call the formula for the washer's method, and this is one that is used when we are rotating around a horizontal axis, and the region that we rotate is not attached to the axis, so that it creates a hole.